All right, you guys, Venn diagrams and set operations 2.3. What are we going to do here? We are going to understand the meaning of a universal set. You may have heard actually with all these counting of ballots happening that they have the set of universal ballots, right? I heard them keep saying that was a good connection to the real world. Understand the basic ideas of Venn diagrams, use Venn diagrams to visualize relationships, find the complements of a set, find the intersection of two sets, find the union of two sets, perform operations with sets, determine sets involving set operations from a Venn diagram, understand the meaning of and, or use the formula for finding the number of A or B. Okay, A union B, I should have said. All right, so I'm not sure when this book was made, but at the time it says Latinos make up approximately 17% of the US population and pump an estimated 1.3 trillion into the economy each year, equal to the GDP of Mexico, the DR, Guatemala, and El Salvador combined. As Latino spending power steadily rises, corporate America has discovered that Hispanic Americans, particularly young spenders between the ages of 14 and 34, want to be spoken to in English, even as they stay true to their Latino identity. What is the primary language spoken at home by US Hispanics? In this section, we use sets to analyze and answer this question. Okay, so that's interesting. I wonder if that is still true. I do not think this book is that old, so maybe it is. So we are looking at, I wish these were on the same page so that we could see, but let me go back and read that really quick just to make sure we understand. So the graph, so we're looking at the circle graph, the set of US Hispanics who speak Spanish at home, the set of US Hispanics who speak English at home. So we're talking about the red pie piece of this pie graph and the orange pie piece. And then you have a piece that they speak both English and Spanish at home and other, or that's the set of US Hispanics who speak neither Spanish nor English at home. Makes me curious about what they do speak. In discussing sets, it is convenient to refer to a general set that contains all elements under the discussion. This general set is called the universal set. So there's the first big piece, you guys. The universal set, symbolized by U, is a set that contains all the elements. So everything in here. So in this case, U is the set of US Hispanic peoples, okay? Notice how this universal set restricts our attention, and we can divide it into the 4 subsets that we are looking at, okay? So if you look at this Venn diagram, our universal set U, they have blue, I'm now making it yellow. And then they have a set A that is a subset of that universal set. So it says use the Venn diagram in figure 2.5, so over here at the left, so our first example, to determine each of the following sets. Okay, so our universal set. So this is interesting. So it's using all of these different symbols to represent the elements in the set. So our universal set is everything. So it's squares, triangles, dollar signs, M's, and 5s. So that is the universal set, is literally everything in our Venn diagram. Set A consists of all the elements within the circle. So just the squares and the triangles. And then it says the set of elements in U that are not in A. So those are going to be outside of the circle, which are dollar signs, M's, and 5s. So your checkpoint wants you to do the same thing with figure 2.6. It wants your set U, so that is everything in the rectangle. B is everything in the circle. So, and you're going to write it as question B says it wants the set A. So A equals, I'm going to do your curly brackets and put everything on the inside of the circle in your curly brackets. U, same thing. That's how you're going to write that out. And C, the elements of in U that are not in A, which is only going to be the ones on the outside of the circle, but inside the rectangle. Okay, so this next one question we're going to be talking about is asking you 2 questions. We're taking a survey asking students, would you be willing to donate blood? Would you be willing to help serve a free breakfast to blood donors? So those are the 2 questions we're working with. And we drew a Venn diagram. It looks like it's down here at 2.7. Set A represents the number of students willing to donate blood. So how about I do this? We have set A, and that's going to be this circle here. And these are going to be really big on the test, just FYI. And then it says set B represents the students who are willing to help serve breakfast. So that's going to be this circle here. They do not overlap. Okay, so we can already kind of start to analyze this. No students willing to donate blood are willing to serve breakfast and vice versa. That's because this is because those circles don't overlap. All students willing to donate blood are willing to donate breakfast. Nope, that's not it. The same students who are willing to donate blood are willing to serve breakfast. Nope. Some of the students willing to donate blood are willing to serve breakfast. No, because those circles are completely separate, it means no students willing to donate blood are willing to serve breakfast, and no students willing to serve breakfast are willing to serve blood, are willing to give blood. Okay. So, well, that was from figure 2.7. They'll be like looking at all of these other ones. So relationship 1, disjoint sets. This is a word that becomes really important to us. 2 sets that have no elements in common are called disjoint sets. So A and B, that's what we were just looking at. If they were disjoint, they would have been that first one we were talking about, but neither one of them are willing to do the other. Disjoint sets are represented by circles that do not overlap. That's what we were just talking about. No elements of set A or elements of set B. Relationship 2, proper subsets. Remember where in this case, A is completely encircled by B. Okay, so everybody who is in A is also in B, proper subset. And since A represents the set of students willing to donate blood and B represents students willing to serve breakfast to donors, all students willing to donate blood are willing to serve breakfast, but not vice versa, right? Because we have people outside of circle A, but inside circle B. Relationship 3, equal sets. It's the set of exact same students. The same students who are willing to donate blood are willing to serve breakfast. There's only one circle. They are equal sets, only one circle of students. There could be students on the outside that didn't want to do either of those things. And relationship 4, sets with some common elements. Okay, so that means that there are some people that are willing to do both, some people that only want to give blood, and some people that only want to do breakfast. Is nighttime for dinner yet, Arnold? Hold on a sec. Okay, so those are the different types of sets. All right, we already talked about that if you want to read through it more, but let's do a question. And there's going to be a bunch of questions on the test about this. So use the Venn diagram in 2.12, it's over here, to determine each of the following sets. Okay, we want to determine our universal set. So I'm just going to go ahead and make that yellow. The universal set is literally everything in the rectangle, even the stuff outside of the circles. So it includes subsets 1, 2, 3, and 4. Set B consists of elements in the regions 1 and 2. Set B in 1 and or in 2 and 3. I was like, that doesn't seem right. In 2 and 3. So if you look up at the top, I can erase, how about I just erase all of the stuff that's not in B. Oops, oh, that just erased everything. All right. So now if we're just looking at B, it's just 1 and, or 2 and 3. I keep saying 1 and 2. Just 2 and 3 right here. Question C says the set of elements in A, but not in B. I'll highlight that a different color. And then you can also read the answer that the book gives you. It's just going to be these. This is everything in A, but not also in B. This makes a lot more sense when we talk about real situations, in my humble opinion. The set of elements in U that are not in B are found in regions 1 and 4. So the set, I'm going to erase everything again. The set of elements included in U, but not in B, are region 4, so everything on the outside, and region 1. So just everything not in the circle B. And part E, the set of elements in both A and B, I could just make those. It's going to be everything in both circles. Okay. Regions 1, 2, and 3. Oops. Just the middle. I thought it wanted everything in both of them, but it just wanted literally that one letter that was in both A and B. Be careful when you're reading. That is a good, so they already have that highlighted in blue. We'll just go over it in green. You can see how easy it is to misread a question. All right, so checkpoint 2, we're still looking at the same Venn diagram. Part A wants to know what elements are in A. So you would put all the letters that are in circle A. The elements in B, but not A. The elements in U that are not in A. And the elements of U that are not in A or B. Okay, try that. Let me know if you have questions. And we move on to the complement of a set, which is the not there, the prime. The shaded region in figure 2.13 represents the complement of A or A prime. The region lies outside circle A, but within the rectangular universal set. In order to find A prime, a universal set must be given. A fast way to find A prime is to cross out the elements U that are given to be in set A. A prime is what remains. So we'll do exactly what it wants us to do. It wants us to find A prime. In A has 1, 3, 4, and 7. So we'll go to U. We'll cross off 1, 3, 4, and 7. What is left is what is in A prime. Okay. 2, 5, 6, 8, and 9. I think you should be able to do checkpoint 3. Read through more slowly if you need to. The intersection of sets, that's the one that I messed up on last time, just where they overlap. The intersection is where they overlap, the actual mathematic definition here. The intersection of sets A and B written A and B is the set of elements common to both set A and set B. This definition can be expressed in set builder notation as follows. So you can read that. I read this as and, that's just the way I grew up reading it, I read it as what is in A and in B. Okay, you could read it as intersection, A intersect B. Either way is fine. Let's do some examples. Find each of the following intersections. Okay, so what is in A and in B? So did it draw? It already drew it for you, I think, over here. But what is in A and in B, I can highlight for you. So A has 7, 8, 9, 10, and 11. And 8 and 10 end up being in both of those. So then when you look at the Venn diagram, those are parts of the circle that overlap. B, if B is 1, 3, 5, 7, and 9, or if A is 1, 3, 5, 7, and 9, so this is not, that was just the answer to that first one. So let's highlight what they have in common. 1, they do not have in common. 3, 5, 7, these have nothing in common. So there's nothing in that one. Right here. And then the last one is also not. They have nothing in common because we have an empty set, which doesn't have anything in it. So it can't have anything in common. I think you should be able to do checkpoint 4. Like I said, they match up really well with the examples. The union of sets, which you can read as A union B, or A or B is how I read it, because as it says in this definition down here, the union of sets A and B is the set of elements that are members of set A or of set B. That's why I'll usually read it as A or B. And then you have the mathematical definition there, if you care to write that down. Let's go ahead and do some examples for each of the following. Find each of the following unions. So let's go ahead and draw this out. So for A, and for the sake of simplicity, let's just make this A and this B, and we'll make this A and we'll make this B. So 7 is only in A. 8, well, it's going to be all of them anyway, but I wanted to show you what it looks like. 8, 9, 10, 11. 8 is in both. 9, 10, 11. Oh, this is the same question. We could just actually be looking at that other Venn diagram. Okay, so here's the question you're asking yourself. Let's take a look at each of these regions. Let's say this is region 1. Let's say this is the middle is region 2, and this one's region 3. Okay, the question you're asking yourself: is 7 a set of either A or B? Yes, it is. So that counts. So region 1 works. Region 2 is 8 part of A, either A or B. Yes, it's actually part of both, but it is part of either one of them also. So region 2 is also part of this union. And then ask yourself again, is the number 6 part of either A or B? Yes, it is. It's part of only B, but that is contained in either A or B. So actually, all of those elements are part of the union, okay? And notice that they only wrote the 8 and the 10 one time when they rewrote that set, because you only need to write it down once. The second one, so it's always going to be all of them. So the same for the second one. And for C, it's all of them also, except it doesn't have the empty piece of it. So it's literally everything from both sets. All right, and we talked about this, but feel free to read this. So A union not is not, there's nothing. A and the union set and the empty set is an empty set. A or the empty set is just A. So remember, go through here. It should just be everything in both of them except for the empty set. Performing set operations. So this is kind of fun. It gives you some steps and some pointers. Always begin by performing any operation inside parentheses, just like always. Okay. So in this first one, you're finding the union of A and B. And then you're finding the complement. Here, you're finding the complement of A, the complement of B, and the intersection that those two may have. So let's go through the example. Given that U is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's our universal set. That's everything. A only contains 1, 3, 7, and 9. B contains 3, 7, 8, and 10. So it's so much easier for me to just build the Venn diagram. Like maybe it's being a baby, but I like to do it so I can see what I'm doing. So A is 1, 3, 7, and 9. So 1 and 9 are only in A. 3 and 7 are in both A and B. And then 8 and 10 are over here. So that means 2 is just part of the universal set, as is 4, 5, 6 are just outside both circles, even though they're part of the universal set. So A or B, if we look at this first one, do everything in parentheses first, A or B is going to be everything in both circles. So if you want not, I was reading it as prime, you could read it as not, makes a little bit more sense. A or B not is going to be what's left over, right? So A or B not will be 2, 4, 5, and 6. It is not in A and it is not in B. Part B, not A intersecting with not B. Okay, so they found all of the numbers that were not in A, which is 2, 4, 5, 6, 8, and 10. Then they found all the numbers that were not in B, 1, 2, 4, 5, 6, and 9. And then where do they overlap? Well, guess what? It's the same exact answer in this case. 2, 4, 5, and 6. Not A, where does not A intersect with not B? It would have been a little bit of a different Venn diagram if we drew it out, but you can see why it worked out the same from the Venn diagram we had already used. So given the universal set, and I'll get you started on checkpoint 6 by helping you draw the Venn diagram. So A is B and C. So we call that A, we call this B. B and C is actually an A and B. And then B has an extra E. So A is actually a proper subset of B. And our universal is A, B, C, D. So A and D are on the outside. Okay. All right, determining sets from Venn diagrams. Example 7 goes, it's just exactly what we just did, right? It just made a table for you. So I'm not going to reread this to you, but something in A union B is going to be literally everything in both circles, right? Regions 1, 2, 3. A union B not is just going to be what's left over in the universal. That's what we just figured out, like how they used 666. A intersect B is going to be in only region 2 because it's in the middle. A intersect B not is going to be everything not in the middle of that circle, so everything except region 2. Not A intersect B is only going to be region 3, what's only in B, not the intersection piece of it, not the A and B. And then lastly, A union not B A union not B is going to include everything except, so the set of elements that are in A or not in B or both. So it's just not going to have things in B. Checkpoint 7, using this Venn diagram. I want you guys to try this. I don't know if there's any way I can get you started without giving it away because they already drew your Venn diagram. So, you know, A is where they overlap. B is everywhere else that they don't overlap, just everything we did. A or B is everything in both circles. A or B not is just everything on the outside. A not union B is a set of elements that are in B or not in A or both. In B, not in A, not in A or both. And then we have all the elements in A intersecting with elements not in B. And you can just read that. I didn't realize this was still just right up here. It's late, you guys. Up here. All right, so going back to that original problem that we started in. They drew their Venn diagram. So they have Spanish speakers where we usually have set A, whereas region 1. Region 3 is they only speak English at home, and region 2, they speak both languages at home, and region 4, they speak neither of those languages at home. And then it's just giving you some formulas if you'd rather use those. I don't think you're going to need them for the test, but we can go through this example. Some of the results of the campus blood drive indicate that 490 students were willing to donate blood. 340 students were willing to help serve breakfast. 120 students were willing to donate blood and serve breakfast. How many students were willing to donate blood or serve breakfast? So this is the same like when we do probability. So we have all the numbers in A and we have to add up all the numbers of B, but then we subtract out where they overlap so they're not counted twice, okay? Or else these 120 students would actually be counted twice. So in all, there are 710 students. That we're willing to do one or the other or both of those, okay? So to help you get started in checkpoint 8, according to factmaster.com, 26 presidents had dogs, 11 had cats, And 9 had both dogs and cats. So we have to subtract out that 9 because that's an overlapping number. How many US presidents had dogs or cats in the White House? And that's going to be 28. All right, you guys, let me know if you have any more questions.